Thank you all for being here today. And so what I want to talk to you about is basically 2/3 of my thesis project. So I'm going to be talking about a program where we're getting parallaxes using Spitzer. So we're getting parallaxes of Y dwarfs. And then the other program that I want to talk to you about is the working on upgrading the NIRSPEC instrument at Keck. And so before I get started, how does the clicky thing work? Sorry.
You can't just.
Okay, I have to click on it. I can't do
Really?
the tab thing, but yeah, it's okay.
Okay.
We're good. So, okay, before I get started, I want to go ahead and give a big thank you to all of the people who have been essential to helping me get through graduate school. In particular, my thesis advisors, Ian McLean and Mike Fitzgerald, but also Davey Kirkpatrick and Chaz Beischman over at IPAC. I've worked very closely with them, as well as a large group of people in the UCLA Infrared Lab, at Keck Observatory, and also a team of people from Caltech working on the laser cone. Okay, so I want to talk to you today about sort of some really big questions that we have in brown dwarf science and in sort of how we understand cool stars, brown dwarfs, and exoplanets, and sort of attacking all of these big unknowns that we have from multiple directions. And so I think some of the biggest questions in our field right now are, we don't currently understand star formation at the lowest masses. I mean, I think that there's some big questions that we have, such as, is there a low mass cutoff? And also, how does star formation efficiency work at the lowest masses? We also have a not fully complete picture of what the solar neighborhood looks like at the lowest mass end. And so we're searching for more objects out there that could be some of our nearest neighbors. And then lastly, I think, and very interestingly, we don't really have a good grasp of the coldest atmospheres and what is going on, because there's so many molecules and there's a lot of interesting chemistry and physics that is going on inside these very gaseous giants. And so I think that's still a very big open question, is probing what is going on inside these atmospheres. And so there's really 3 ways that we can go about answering these questions. So first, we can, of course, go out and take observations of these objects, and we can use primarily infrared observations from space and from the ground with spectroscopy, photometry, and astrometry. And that can kind of tie back in with atmospheric and evolutionary models that we have. But then likewise, the observations tie back in with our development of new instrumentation. So when we go out and we take observations and we find something really interesting and we want to further explore it, this kind of tells us which direction our instruments should be developing, so that in the next round, the next generation, we know where we want to go. And so for my thesis, I've basically focused on 2 fronts that I'm attacking these problems from. And so the first would be taking observations and trying to understand those observations. And the second is instrumentation development. And so my talk today is going to be in 2 parts. And the first part is going to be about some observations that we took with Spitzer. And then the second part will be about instrumentation development that we're doing in the lab at UCLA. So to get started, the project in which we were measuring trigonometric parallaxes using Spitzer, I want to go ahead and, before we dive too much into the methods, I want to go ahead and give a brief overview of some brown dwarf science, just in case there's people in the room who are not super familiar with it. So brown dwarfs are substellar objects, which means that their masses are under about 75 Jupiter masses. And what this means is that they also all have radii about 1 times the radius of Jupiter. And then what this means is that they're also very cold objects. So when we talk about brown dwarfs, we mean objects, cooler than about 3000 Kelvin. But here in my talk, I'm going to focus on objects that are late T and Y dwarfs. And so these are colder than 1000 Kelvin. And then that has implications for what's going on inside their atmospheres. And so we've got interesting molecular species that are being formed in clouds. There's the potential for non-equilibrium chemistry going on because of mixing, etc. And then until very recently, brown dwarfs have been extremely hard for us to find. And that's because if you take a look at the Stefan-Boltzmann law, the fact that they're small and cold therefore means that they're faint. And so really this is where using the advent of infrared technology has allowed us to first discover these objects and then begin to characterize them. And so when we think about mapping out the solar neighborhood and sort of the motivation for this project, we can take a look at our current understanding of the solar neighborhood, and even just within the closest few parsecs, this picture has vastly changed within the last couple of years. So, oops, I'm breaking things. Okay, sorry. So if we look at the nearest few parsecs to the sun, you know, we've got Alpha Cyn and Proxima Cyn and Barnard Star, which were all discovered in the early 1900s, but only within the past couple of years, we've got a new LT binary as well as a new Y dwarf, all found, you know, in 2013, 2014. And I think that this picture is going to continue to change as we continue to do these proper motion surveys using telescopes like WISE, et cetera. And so that's why completing a volume limited sample using Spitzer to find parallaxes, that's going to help us determine where are all of the other closest neighbors that we didn't know were out there before. And then if we want to take a look at understanding star formation at the lowest masses, parallaxes are also important because the distances allow us to probe the absolute physical properties of these objects that we're finding. So if we take a look at a plot, actually this one on the left is from Trent's paper in 2012. If you take a look at absolute magnitude versus spectral type, if you think of spectral type as a temperature sequence, which it sort of is, you can see that the absolute magnitude in the J band is dropping, but by the time we get to the Y dwarfs, it's starting to drop really, really significantly. And we kind of have an unclear picture of what exactly is going on here because we have such a small sample. Additionally, if we were to take a closer look at a paper from Marsh et al. In 2013, and this time look at absolute H band magnitude, you can again see that as you move into the Y dwarf regime, that the absolute magnitudes are just really dropping off. But there is this really big unknown space here, and we don't really know what kinds of physical parameters we're probing here. And then with these physical properties, once we can determine a temperature or some kind of proxy for a mass, we can start to look at the low mass end of the field mass function and start to characterize the shape of it. And that will tell us about, you know, the efficiencies of like how star formation works at the very lowest mass end. So this is a plot from Davy Kirkpatrick's 2012 paper in which he's plotting the number of objects per 100 Kelvin bin within 10 parsecs. And so if you take a look at the late T's here, they're fairly certain on just how many objects within 10 parsecs there are. But when we go to the Y dwarfs, all we have are lower limits. And so really it's taking a look at finding all of these objects and figuring out how many of them are within a volume limited sample, we can actually vastly change, even just the addition of one more object can vastly change the shape of this curve. And as you can see, it definitely does not match up with you know, the traditional sort of power law models. And so there's definitely going to be a lot more to understand here about what exactly is going on. And then lastly, as far as understanding the coldest atmospheres, parallaxes again are really, really important. And brown dwarfs also are really important because brown dwarfs allow us to make a really good comparison to exoplanet atmospheres. So as you all probably know, exoplanet detection and characterization is really difficult because of the having to block out the light from its host star. But you can think of a brown dwarf, many of these brown dwarfs, as basically a free-floating giant exoplanet. They're going to have very similar temperature and mass and similar chemistries going on. So what I've got here are 3 different model atmospheres. This one is from HR 8799c, which is at 1100 Kelvin. It's a young giant planet. And then we've got a field T dwarf, and then we've got Jupiter. And you can see that they all have very similar species located within their atmospheres. Now, there are some differences in locations of cloud decks, and I'm sure their compositions are also going to be different, but when we start to test the atmospheric models with the brown dwarfs, then once we have really good exoplanet data, we'll be able to make some more informed understanding of that. And then brown dwarfs also allow us to compare the small amount of exoplanet characterizations that we can do to actually try to start looking at things like gravity and temperature and metallicity. So this is the spectrum that was taken by the GPI team of 51 Area B, and you can see that they basically have a resolution of about 50. And they're actually quite noisy as well. But even with these data, they're able to make comparisons to field brown dwarfs. And with that, they're able to say something about the kind of temperature and gravity of this exoplanet. All right, so because these brown dwarfs are so cold and so faint, we really need to turn to the mid-infrared in particular. Especially once we start getting into the wide dwarf regime, doing this from the ground becomes very, very costly in terms of the amount of time that you need to observe these objects. So what I'm showing here are two atmospheric models from Caroline Morley's 2012 paper, in which she's comparing a late T-dwarf at about 900 Kelvin and a wide dwarf at about 400 Kelvin. And you can see how the WISE W1 and W2 and the Spitzer channel 1 and channel 2 filters are actually very nicely chosen, such that most of the flux in this 4.5 micron peak actually comes out in the W2 band. And so you can get really, really bright, the objects are really, really bright in the Spitzer and WISE bands, which makes them really nice instruments to use for these objects. Now, and this is something that I think has been kind of surprising to people, which is that you can actually do precision astrometry with Spitzer. And I don't think that when they originally built Spitzer, they were thinking that this was something that would happen, but it is actually possible. And part of the reason this is possible is because these objects are so very close. So what I'm showing here is what we call a super mosaic stack of the Spitzer images. And so these are basically every single frame that we have for one particular target stacked on top of each other. And this is WISE 0410, it's a Y0 dwarf. And if you zoom in on the middle of that object, you can see the object that I've circled in green kind of looks like fuzzy and extended, but it's not a galaxy, it's the brown dwarf. And it's just the fact that the brown dwarf is moving so quickly through these images that even with a time baseline of only 3 or 4 years, we're actually able to see that big motion across the field. And so once we pull out the proper motion, we are able to get a parallax, again, because these objects are so close. Even though our positional uncertainties are high with the Spitzer pixels being so large, we're still able to get precisions down to about 10%. So with that in mind, Davey Kirkpatrick and some of his collaborators, and I jumped on later, designed the Spitzer Parallax program. And the point of the program is to measure precise distances to all of the T6 dwarfs and later, so that they could complete the low mass end of the field mass function with a volume limited sample out to 20 parsecs. And included in that was distances for all known wide dwarfs, because even the ones that have been measured from the ground, we wanted to have a second observation of these. And so with that, we started taking Spitzer observations back for some of these objects as far back as the mid-2000s for some of the two mass discovered T-dwarfs. But most of these objects were discovered with WISE, and so we have data since about 2010. And so what we've got are IRAC channel 2 frames taken at maximum parallax factor over baselines greater than 2 years. And we use the APEX routine that was provided by the Spitzer Science Center to determine our centroids. And as part of this centroiding process, we actually used a custom point response function that was created for us. So basically, the pixels on Spitzer are so large and you're undersampling the point spread function that actually what you need to do is you have to also include basically how the pixel responds differently across, one spot of the pixel might actually be less sensitive than another spot of the pixel, and that will affect where you think your centroid is going to be. And then after we've applied this correction for the point response function, we also use the Spitzer 5th order distortion correction, which accounts for the fact that there's optical distortion on the field of view of the detector. So once we have our centroids, then we want to re-register everything onto a common reference frame. And so we were really lucky in that Gaia DR1 came out right when I was working on this project. And we said, why don't we, instead of, because the traditional thing to do is to align probably to 2 mass, but we said, why don't we use Gaia? Because the Gaia positions are really, really good. They're less than about a milli-arcsecond in most of the cases. And so sure enough, in pretty much every single field, we end up with several, anywhere from about 7 to as many as I think 70 or 100 Gaia targets in our field of view. And so in every single frame, we can go and realign each frame so that it's onto the same Gaia reference field before we, and so we can adjust the centroids that we calculate. And then we also had to redetermine the positional errors of the centroids that we were getting for our targets, because the apex routine spits out these very large positional uncertainties that we feel were just really too pessimistic. And so what we did is I did a comparison of basically the repeatability of the reference stars in the field. And so what you can see here is this is the uncertainty in the position that we measure across all of the epochs as a function of signal to noise. And you can see that once we get up to really high signal to noise targets, our positional uncertainties kind of plateau here. And that ranges from about 15 to 30 milliarcseconds, depending on the field of view and how many reference stars there are. And our targets all have very high signal to noises. And so we actually use the estimate of the median here as our positional uncertainty. And so for most of our epochs, we've got positional uncertainties on the order of about 15 milliarcseconds. So once we've got all of our centroids and all of our positions, we can then start to fit for both the parallax and the proper motion. So what this movie is showing is WISE 0410. Again, this is the Y dwarf that I was showing earlier. And you can see basically the motion of the object through the sky kind of zoomed in. And so every single one of these blue points is an observation that we took. And then the black line is basically the best fit model for that. And it's a little bit hard to see on this plot, but you'll see it in later plots. There are tiny little red lines that represent the time distance between the observation and where the object would have been on that curve. So if we pull out proper motion, then you end up with a parallactic ellipse where you've got delta declination and delta RA here. And so you can see here these red lines that represent where this observation would have lied on that best fit curve. And what you can see is, so for this particular object, it's located at about 6.5 parsecs. And we've actually got a really low uncertainty on this. Some of them are, below 5% uncertainty. Some of them are higher, especially the ones once we're getting closer to 20 parsecs. And then as part of this program, we ended up with some confirmation of 3 new late T dwarfs. So we had some objects on the program that were thrown on because of their WISE colors. So we were pretty sure that they were brown dwarfs, and so we went ahead and put them on the Parallax program, but we didn't actually know. And so I was a visiting grad student at IPAC for a semester, and when I was there, we took some NIRSPEC observations of these objects to confirm them, and one of them ended up being a galaxy, and so we had to throw that off the program, those pesky AGN. But we did end up with 3 new T dwarfs, and so we've got a T8 dwarf that ended up being at about 22 parsecs. We've got a T8.5 at about 20 parsecs, and then we've got a T9.5 at about 13.5 parsecs. And I think this is really exciting because we thought we knew really well how many T dwarfs there are in the local neighborhood, and I think that is slowly changing. We also had a really exciting kind of serendipitous discovery. There was an object that we had on our program that had very red WISE colors, which is an indication that it's probably very cold. And Greg Mace, who had been at UCLA and worked at IPAC, had taken a spectrum of the object back in 2011, which is shown here in gray. And the best fit standard to that object was a T8 dwarf. But it was a very noisy spectrum, and so we decided to go back and take another spectrum and see what we could see. And this object is really, really faint. Its J magnitude is fainter than 22. And so this is really pushing the limit with what you can do with NIRSPEC. But we managed to get a very low signal to noise spectrum. And this time around, it actually looks like it's somewhere between a Y0 and a Y1. And this is, I think, a really confusing thing. And the best that I can come up with to explain how this is happening is that there must be some kind of large hotspot or something on the object. And so it just happened that when Greg observed it, the object appeared to be much hotter than it actually is, because sort of based off of the WISE colors, we don't really see that there's any way that this object could be anything other than a white dwarf. But so that's pretty exciting. And then, of course, because it's on the Parallax program, this white dwarf is actually just inside 10 parsecs. So we're pretty excited about this new target that we have. All right. So I want to go ahead and come back to the motivation and the science that we're trying to get at, and sort of thinking about what are the answers that we can come up with from this project. And so first, as far as mapping out the solar neighborhood, so we actually have 22 objects on this Spitzer Parallax program, and we have updated parallaxes and new parallaxes for a handful of objects. And so now we've got a much more precise look at what exactly, who exactly are our closest neighbors and what's going on. As far as the star formation question and the field mass function, we can actually start to update this function. So we've got new objects in the Y0 bin and also in the Y1 plus bin that are going to completely change the shape here. And then actually not in the paper that I'm writing, but in Davy's paper, it's looking like there are going to be a lot more T-dwarfs than we had originally thought. And then as far as understanding the coldest atmospheres, I think this is where some of the most exciting stuff has come out of this paper, which is now that we have absolute magnitudes for these objects, we can start to look at some of the trends. And so when we fill in the absolute magnitude versus spectral type plot, before this was a lot of just empty space and we weren't really sure exactly what's going on. But now we can start to see that, well, first off, as you would expect, absolute magnitude is decreasing as your temperature gets colder. That's good, physics works. But there's a pretty big question about what on earth is going on with these white dwarfs and why do they have such largely varying absolute magnitudes. In order to better understand that, we're actually going to turn to looking at the color magnitude diagrams. But I'd just like to point out that it seems very bizarre to me that objects that have very similar looking J-band spectra would have, and so therefore you assume they have very similar temperatures and very similar, well, mostly just temperatures, would have 5 magnitudes of difference in their absolute magnitudes. So that to me says that we're not actually probing temperature when we're looking at spectral types in the white dwarfs. So if we look at the color magnitude diagrams, here I've got absolute J and absolute H versus J minus W2 and H minus W2. You can see that there's a much tighter trend here. So to me, what this says is if I'm looking at the J minus W2 plot, if we go back to this one, if you think that spectral type is probing temperature, you would expect a much tighter correlation between those things. And that's really what we're getting when we look against the J minus W2 color. And so I was looking at Adam Schneider's paper that came out in 2015, and he had plotted up some of the atmospheric models. And sure enough, the J minus W2 color does actually trace the temperature of objects. And so there is definitely some spread here, depending on whether you're looking at 100% cloudy or cloud-free, which model you're using. But as you go colder, your object gets redder, which again makes a lot of sense. So if we turn back to the absolute magnitude versus spectral type plot, but this time we color the objects by their J minus W2 colors, where the hottest objects are in blue and then the coldest objects are in red. Then you can see that basically the J minus W2 is probably tracing out a temperature sequence. And so then what we're looking at is all of these objects that we're calling Y0 objects are probably not similar temperatures. We're probably looking at a pretty large temperature range. And I think that the reason that we have sort of not been able to see this before is because we're really looking at the Veen tail of the black body function, right? So these objects are so cold that their peak has shifted all the way into the mid-infrared. And so if you're only looking at a tiny little opacity window where some light is coming out far on the Veen tail, then there is possible that you could end up with vastly different temperatures that are looking sort of similar in that range. But if we were to move further into the mid-infrared to start doing our spectral classifications, then we probably are going to get a better understanding of the temperatures that we're talking about. So in the future, we are currently collecting our cycle 13 data and probably going to submit a cycle 14 proposal to continue getting astrometric monitoring of these objects. And also included in that will be a more detailed look at the field mass function. And then I actually have some time coming up this Saturday to get Keck NIRES data of these objects. So NIRSPEC in its low resolution mode isn't quite sensitive enough to get some of these really faint objects, but NIRES does simultaneous 1 to 2.5 micron spectra at R of about 3000. And I'm really hoping for good weather because last observing was very poor weather. And then lastly, I think that looking to JWST, we'll finally be able to get really good spectra in the 3 to 10 micron range. And I think that's when we're actually going to be probing things like temperature and gravity of these really cold white dwarfs. So I'm going to put up the summary for part 1, and now would be a really good time to take any questions for this part before I move on to the instrumentation component. Yeah.
Just a very naive question. So the spectral type is based on just the optical colors?
No, so the spectral type it depends on the brown dwarf. So like originally, like with M dwarfs, they were spectral typed in the optical, and then when they got infrared data, they also came up with an infrared spectral typing system. Traditionally, the spectral typing has been done in the J band because the models have shown that the J band is the most sensitive to temperature and insensitive to other things. So you should hopefully be probing mostly temperature. And there's several different ways to go about spectral typing it. Like people have come up with spectral indices that you can measure. And I would say like one of the most common methods is just a by eye method. And so you compare a standard to your observation and see which standard it fits the best. Yeah.
There are very few white dwarfs though, so the whole classification of white dwarfs is in its infancy.
Yeah.
But on the same question, now if you have such a variation in temperature for the T dwarfs, doesn't that mean that essentially the spectral typing is not correct?
Yeah, I mean that's basically what I'm saying is that we're doing the best that we can with what we've got now, because right now the only spectra that we can take of these objects are with HST or with a 10-meter class telescope. But once JWST launches and we have the spectra in the mid-infrared, I think we're going to completely redo the sequence and hopefully start understanding a lot more about these objects.
Unfortunately, once JWST dies, we'll be back stuck with near-infrared measurements.
Don't say that.
Emily, the mass function, I know it's more Davy's paper, but do you think it's going to look almost like a flat mass function then?
I don't think it looks flat. I think it still has a bump there, but
the bump at the end?
Yeah.
I mean, going up?
That it's going up.
It goes up and then comes back down. Yeah.
Oh, okay.
Yeah.
Yeah, I couldn't tell because you had arrows there on the last two bends pointing that it was going.
It is going up on the far end. Yeah. But so Davey has a student right now who's running some models and yeah. All right. So I'm going to move on now to part 2 of my talk, in which I talk about work that I have done working in the UCLA infrared lab to upgrade the NIRSPEC instrument for Keck. So to give you a very brief overview of NIRSPEC, first off, I apologize for the very old mechanical solid drawings. So NIRSPEC was originally commissioned in the late 90s, and upgrading it has been an adventure because all of the documentation, all of the drawings were done in like the original AutoCAD and not in SolidWorks. And so it's been an adventure, like porting everything into like more updated software to try to understand what's going on. But in any case, NIRSPEC is a 1 to 5 micron, a shell spectrometer, and it has capabilities of doing both high resolution at R of about 25,000 and what we call low resolution, which is really more medium at R of about 2,000 or 3,000. And so light comes in here from the telescope. It goes through an image rotator, which takes care of the fact that the sky is rotating from our point of view. Any light that does not go through the slit actually comes off into a slit viewing camera so that you can more easily align your target onto the slit. Then the light is collimated here, and it passes by both in a shell grating and a cross disperser grating, and then it ends up becoming imaged by a 3-mirror and a stigmat here, and then this is the science camera here. So as I mentioned, NIRSPEC was commissioned in 1999. What that means is that a lot of the technology that NIRSPEC uses is actually from the early and mid 90s. And so the NIRSPEC upgrade, the goal of that is to bring NIRSPEC into a more modern era. Infrared technology has advanced a lot, and so have electronics. So what we want to do with this upgrade is the first and most important thing is that we want to upgrade the spectrometer detector to a Hawaii 2RG from Teledyne. So the current detector is an Aladdin 3, and it's got 1024 by 1024, 27 micron pixels. But the new detector is going to have 18 micron pixels, so smaller pixels. It's still got the 5 micron cutoff, but it's got much better noise sensitivity. And so it's going to overall be a much nicer detector. The second thing we want to do is replace the slit viewing camera so that it can operate all the way out to 5 microns. So the current slit viewing camera only works out through K-band. So if you have a very embedded object or something that you want to observe and get L and M band spectra with, you actually have to put the target on the slit in K-band and then hope that the differential atmospheric refraction is not going to mess you up too much, and hope that the object will still be there when you change your filters into the L-band to take your observations. So this has been a big call from especially like the comet, people who observe comets and people who do debris disks and other kinds of like embedded objects. They really want this ability to operate out to 5 microns. And so the new NIRSPEC upgrade is going to have that. And then the other really big thing is going to be updating all of the control electronics. So NIRSPEC runs on these things called transputers, which I thought was some like made up sci-fi word from like the 1970s, but turns out it's a real thing. And so we're actually going to be getting Galil motion control. We're going to have updated all of our control electronics, all of the readout electronics for the detectors are new, and then the software will also be updated. And then the last 2 things that we're doing to NIRSPEC are designed to help improve the stability of the instrument. So people using the high resolution portion of NIRSPEC, a lot of them are looking for precision radial velocities. And the problem right now is that NIRSPEC is not a very stable instrument because it was not originally designed to be a precise radial velocity measurer, but now people want to use it as such, and so we need to make some modifications. So the first thing that we're going to do is we're going to improve the stability of the shell grating turret. So the shell grating is a very large thing that sits on there's a large motor that runs it. And it's perfectly stable, like it's like perfectly balanced, so that once you move it into a position, it just sits there. But the image rotator is a very large thing over here in the instrument, and every time you have the image rotator running, it's going thud, 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 thud. And every time it does that, it shakes the shell grating enough such that your spectra on the detector actually move by pixels. So we're not even talking about subpixel movement here, we're talking about pixels, which is really bad if you're trying to measure radial velocities. So we're going to fix that by preloading the motor mechanism. And then the other thing we're going to do is add some temperature control to the main instrument bench. So currently inside the main dewar, we actually are just running the cold cycle refrigerators, the CCRs, full out. And so if the dome temperature fluctuates by a few degrees, then NIRSPEC's temperature fluctuates by a few degrees. And so we'd rather keep that much more stable, because temperature fluctuations mean that things are moving around inside the dewar, and if optical components are moving around, that means your spectra are moving around on the detector. All right, so as part of my work in the lab, I've done a lot of optical design work. And so when I first started working in the lab, I was looking at the expected performance of the new Hawaii 2 format. So the Aladdin detector format is actually this smaller inner square here. And you can think of this as like image space. And then the Hawaii 2 is actually the larger square here. So it's got 4 times as many, 4 times as many pixels, but it's got smaller pixels. And so you don't end up with quite as large of a, like it's larger, but not extremely larger. And so what you can see here is basically every single one of these lines represents an order on the detector. And then along these diagonal lines, that represents along one of the slits. And so I assessed the image quality, or basically the spot size, at different locations, because we saw that we'd be getting all of this extra new space around NIRSPEC, and we wanted to know if any of it was going to be viable. And turns out that actually most of it is. So here on the edges, at the sides, and the top and bottom, the spot sizes are actually close to or under the size of 1 pixel. So that means we're going to be getting optical quality that's good enough that you can use it. However, at the corners and the, at all of the corners, basically the spot sizes end up blowing up. And so your image quality has degraded and you won't be getting anything useful there. We also have some vignetting here. So that's what the fainter spots represent vignetting. And so some of the light isn't making it through just on the very corners of the detector. But so what this means is that replacing the detector with the Hawaii 2RG, we're not changing any of the optics or anything like that, but we are going to end up with smaller pixels, which means that if you're slit limited, you have higher resolution, and you're not actually going to have any losses. You're only going to gain footprint, like actual amount of spectral grasp that you have, and you're going to gain in resolving power. So we have also done testing or simulations of what we expect the performance improvements to look like. And so the dark current is decreasing significantly. There's a small increase in QE that's almost negligible, but then the read noise is also significantly decreasing. And so what this means is that particularly in the J, H, and K bands, which are shown here in the blues and greens, you're actually going to get more than an order of magnitude in signal to noise for the same time exposure for the same object. Now with the L and M bands, you're still largely background limited, so there is a small increase in terms of how sensitive we are, but because the thermal background is so high, we're not detector limited there. But still, this looks really good because you're actually going to be, in the J, H, and K bands, be able to observe objects up to a magnitude fainter, which is really exciting. So we have successfully prototyped our detector head assembly, and we've successfully tested a test detector that we've got, and now we're actually, when I get back to UCLA, we're going to be installing the actual detector and start cold cycling that. But so this is basically what it looks like inside of our test chamber. So this outer wall here is the outer wall of the dewar, and then you see the cold shield here. And then this box is basically the entire detector head assembly. And the detector sits just on the inside of this copper block. So it's cooled by attaching the copper block directly to the closed cycled refrigerators. The detector runs at about 30 Kelvin because we need to operate all the way out to 5 microns. And then the silver box that's sticking out below, this is the readout chip. So this is the ASIC. And then that connects via ribbon cable to a hermetic seal here, so that there is another piece of readout electronics that converses with the computer. And so we actually have a much nicer readout electronics system. And so all of this has been tested many, many times, and we are very pleased with our results and excited to move forward with the actual detector. And then another project that I've worked on pretty extensively has been the optical design for the slit viewing camera, or SCAM, which is a terrible name, I will admit. And so this is basically a view of how the SCAM works. So you have your slit surface here, and any light, so light is coming to a focus at the surface of the slit, and any light that does not make it into the spectrograph because it's not going down the slit is actually being reflected off of this surface because the slits are all gold-coated mirrors. And so then that light bounces back onto a fold mirror and into a separate mechanism that we call the slit viewing camera. Now, the old slit viewing camera uses a picnic array, which I actually recently found out is older than the NIC-MOS arrays. So we're talking about really old infrared technology. It's a 256 squared. It breaks down a lot and has ginormous pixels. But so what we wanted to do was basically make SCAM viable all the way out to 5 microns. It turned out to be a much trickier problem than we were originally anticipating, because we had to keep the mechanical size of the slit viewing camera within the exact same space, right? Because we're not altering, we can't change the size of the doer. And so we're very much constrained by the mechanical space of that. And the other thing is that we are moving to something that moving to a detector that has pixels that are more than 2 times smaller than the current detector, and we want to more than double the wavelength range. And so this actually meant kind of a tricky optical design problem, but I was finally able to come up with a working design. And so when we've got light coming in from the fold mirror here, it goes first through a collimator, and then we actually had to add another filter wheel to the slit viewing camera. These Teledyne detectors are so sensitive in the LNM band that you're gonna completely blast your detector with thermal background in the LNM bands if you don't have basically like a very narrow band pass filter, so that only a small amount of the LNM band light can make it onto the detector. And then finally it goes through a 5-element camera and focuses onto the Hawaii 2RG array. And so tests of the spot diagrams show that the pixel sizes or the spot diagrams are well within 1 pixel. So this is an 18 micron box here. And this is the on field. And then we've got 2, let me see, this is a corner and a side. And so basically all the way from 1 to 4.5 microns or 4.6 microns, right in the middle of L-band, we're getting really good optical quality. And one of the other ways that we were testing the optical quality was looking at the encircled energy. And so you want to think about how much of the energy of your incoming light is making it into 1 single pixel. And so we set a requirement of 80%, and we are meeting that in all of our fields and across all of the wavelengths. So the next step with the slit viewing camera is we're actually just this week placing our order for the optics, and then those will arrive probably within about 2 to 3 months, at which point we'll begin aligning them and putting that all together. And then the last major component that I've been involved with with NIRSPEC has been actually looking at bringing NIRSPEC into the future of precision radial velocity by testing a laser frequency comb. So you will probably start to hear about laser frequency combs a lot as precision radial velocity, test follow-up, et cetera, becomes a really big hot topic. And the basic gist of it is that you have a laser that goes into a cavity, and basically you end up pumping it such that you have perfectly spaced laser lines that are perfectly spaced in frequency space, and you can measure them to extremely high stability. And then if you shine that light onto your detector at the same time that you're taking observations, you end up with a perfect wavelength calibration that is evenly spaced all across your detector. So we tested this back in 2015 and 2016. And then again, this last fall, we tested a new laser comb, which is an even more exciting one that's broader and even more stable, called a soliton comb. And so what I'm showing here is basically this is a these are raw NIRSPEC data, and the only thing I have done to them is rectify them spatially and spectrally. But you can see that across pretty much the entirety of the H-band in one single image of only about 20 seconds, you're getting, 100,000 plus ADU in some of these orders of perfectly spaced lines where you can measure basically to the 30 centimeters per second level, the wavelength. And so you end up with a really, really nice wavelength solution. If you compare that to the neon, argon, et cetera, lamps, where you end up with, maybe somewhere between 3 to 5 arc lamp lines per order, this is vastly increasing the kind of wavelength solutions that you can get.
How do you absolutely wavelength calibrate it?
How do you absolutely? Oh, so you would have to use, well, actually, so if you see the central line here, where it's been kind of damped down, so that's actually the F0 of the laser, and so they know that very precisely. And then you also can measure your delta F, basically through the way that you work the laser comb. I don't know too much about that, but then the other thing that you can do is you can take arc lamp lines. So you can say, okay, this lamp is here and this, the laser comb line is here, therefore it must be this wavelength. And then from that, your delta F and you can compute all of them. And okay, yeah, so to finish up, the NIRSPEC upgrade is coming starting in 2018B. So I'm gonna be out here probably in the fall a lot installing that, which I'm super excited for. And after the NIRSPEC upgrade, what this means for you as observers is that you're going to get higher resolution. Now this is slit limited, so if your seeing is really good and you can move to a smaller slit, you can actually get resolutions of 37,000. This means better science and slit viewing camera detectors. You can observe up to a magnitude fainter in the short wavelength ranges. And then the last thing is that a new fiber injection unit combined with the laser frequency comb is going to mean that when you're observing with AO, you can get really precise radial velocities. So yeah, we're looking forward to this, and I'll go ahead and finish up my talk right there.
So all these upgrades will be done simultaneously. So when you bring the instrument back in 2018B.
Right. So the plan is that so NIRSPEC is scheduled all the way through the end of July, and then in August we'll start warming it up. And then we actually are building all of the upgrade components at UCLA, and we're going to ship the detector heads and the new cameras and the new electronics out here. And they're going to take NIRSPEC off the telescope, and then they have a clean room set up in one of the domes. And so we'll be doing all of our service work up at the summit. And so that will probably take multiple cycles in terms of getting the detector just placed just right in focus. But we should be done by the end of December. And then it should be back up and ready to go in 2019.
So at the same time, you have all the new software.
Yeah, the new software, the new electronics, the new detectors, everything all in one go. Now the laser comb we're still trying to get funding for, but that can be added separately more easily because it's an outside calibration thing. Yeah.
So you will still be at UCLA when this happens?
No, I'm gonna have a postdoc, but I'm gonna come back as a consultant for it because I've been working on this project for 5.5 years, and I didn't want to not be able to see it all the way through to the end. Yeah.
Question about are there laser combs operating anywhere yet? Or?
Yes. So actually, I found out that HPF is being commissioned right now on the Hubble telescope. It's the Habitable Zone Planet Finder that Suvroth Mahadevand's team built at Penn State. And this is a near-infrared precision radial velocity. I think they're getting R of like 200,000. And I think they bought an off-the-shelf. No, sorry. They had a special one made for them by the folks at NIST. And then for their NEWID instrument, they bought an off-the-shelf laser comb.
NEWID is when or something?
Yeah, exactly.
So wait, what's the difference between your laser comb and the HPF one?
So the newest one that we tested is called a soliton laser comb, and I don't really totally know all the laser physics at all, but I know that like the soliton is sort of like the next generation's is like brand new, just it's still in R&D basically, and the one that they have is what's called an EOM comb, and so that's been a bit more tested. But I think with the soliton you end up getting a broader spectral range, and then you can use these attenuators to kind of try to get more a flatter level of like light that's coming out, because for the laser comb, like most of the light is coming out in just this one short wavelength range, and then you want to be able to broaden that out so that you're not like blasting the detector in one spot and hardly getting any signal in the other parts.
R equal 200,000?
Huh?
In R equal 200,000?
Something like that.
And the infrared, is it in a shell or
Yeah,
echelon? Or?
Yeah, it's in a shell. I don't know too much more about it, but they're commissioning right now. Yeah.
It's got to be the highest resolution infrared spectrograph in existence.
I think so, yeah. Yeah.
This is not a very scientific question,
It's
but what wavelengths and band passes are you using for these narrowband filters in the L and
Oh, right.
M
So
band?
we're looking at the L prime and M prime, and that's actually,
Yeah.
it's an interesting problem, because we realized that in order to not fully saturate the detector in the minimum exposure time, you actually have to really significantly attenuate how much light
Are
you can
using
allow
neutral
through.
density
So we
filter
ended
or
up, we're combining an ND3 filter with an L prime filter,
Okay.
basically. That was sort of the
Same in
solution
the
that we
M.
came up with.
Oh, and the same with an M.
Yeah, same in the M, yeah. Because we were asking the filter companies if they could make like an L prime filter where you're only getting like 1% of, or less than 1% of the light through, and they're
I mean,
like,
there are narrowband bracket alpha filters and things like that.
right. Yeah, I think we wanted a broader band pass, but then to cut that down, so.
Still catching up with the first half of your talk.
Oh yeah.
So you fit these parallax ellipses, but sometimes there's a point with relatively small error bars that's nonetheless a long red line away from the fit.
Yeah.
So is this a simultaneous fit of the time and?
Yeah. So you have to simultaneously fit. So you fit the initial, like, so you have an initial time point that you want to fit through. So you have like an alpha naught, a delta naught, and a T naught.
Yeah.
And then in addition to that, you're fitting your parallax and your proper motion in two directions. And so kind of within those equations, the time is part of that.
Yeah.
And then you also need the information from the Spitzer Space Telescope, like it's X, Y, and Z in space. Because what it's going to be seeing is different from what we'll be observing from Earth.
Yeah, one of the cool things about this is doing parallax. It's the only time I think in astronomy we do parallax is not from the Earth.
Yeah.
Right.
Spitzer sometimes is closer to Mars or Venus than it is to us. Well, I don't have Mars, Venus. Not Mars, sorry, Venus. Sometimes it is, it depends, because Spitzer's getting farther.
It's getting farther and farther away because it's in an Earth-trailing orbit. And so I think cycle 14 might be the very last one they can do before they have to shut it off. But in something like 50 years or something, it's going to come back into being very close to Earth again, which is cool.
Any other questions? If not, let's thank Emily again.